So let's start very, and this is quite mathematical. So what I'm going to do is I'm going to be very slow so that you understand. And it's also important that you ask me as many questions as possible. That way I'm able to know what is in your mind, and then I can explain it well for you. If you can understand, let me begin. So we are going to make a very foundational assumption that we have a production possibility set. The production possibility set is similar to the technology set. So we are going to make an assumption that we have something like this: X on the x-axis, Y on the y-axis. And then if we assume constant returns, the graph will look like that. Okay. And if we assume constant returns and the graph does look like that, then it means that all the information will be contained inside this very graph. So you have the observations, all of them, inside. So the whole thing that you see plus the line is a technology set. However, if the graph were to be, a graph that is like VRS, okay, VRS graph will look like something like this. Let me see. Okay, it will look like something like this. Then it goes that way. Then it goes that way. And finally, so you have something like VRS. Right. So that becomes the technology. So what that means is that everything else that you see, okay, in this hat, okay, will not exceed the VRS frontier. It will be at the edge or tangent to the frontier. So they will be there. So the technology set is made up of the inputs and the outputs that have come together to make up the DMU. That is the technology set. And I want you to understand this in total, because when we bring the mathematics to it, it might be slightly confusing to somebody who doesn't understand, graphically. All right. So we are representing this technology set by this Greek letter phi. Okay, that's a capital letter for phi. Okay, and this technology set, which is the phi, is made up of certain things which are n. These n are the number of the DMUs. So all the many DMUs that you are, seeing, all of those many DMUs, all put together are the n. But for us to achieve a DMU, and this is important, this is interesting, okay, and I'm trying to make it as practical as I could, okay. In order to have a DMU, okay, certain things make up a DMU. So before you tell me that A is a DMU, I must have an input, which is x1 of A, and then I must have an output, which is y1 of A. Okay. So A will be made up of the coordinate x1 and then y1. That is what make up the A. So when you see A, okay, A is a DMU, but what makes it a DMU are the inputs and the output. Now, in the DEA parlance, the language that you use for the input is M. Okay, for each of the input, you are calling them M. And these inputs are many, so they start from I, okay. Each one is an I, we start from 1 all the way to S. Okay. Oh, sorry. Each one is, each of the input is an I. Okay, let me just go back and show you now. Each of the input is an I, and the I starts from 1 all the way to M. So there are M number of inputs. So if you take a bank like this, the bank will have maybe 5 inputs. 5 inputs. So M is equal to 5. Okay. The 5 inputs will be made up of 1 being deposit. Okay. So one of the inputs become deposit. Another input become labor. another input become capital, and then on until M, where M is the total number of inputs. So when you see I is just one of the inputs, and M is the total number of inputs. Now, if we have I, which starts from 1 to M for the inputs, then we also have R, which starts from 1 to S for the outputs. So the outputs are, each output is an R, and they start from 1 up to S. So S becomes the total number of the outputs. What about the DMUs? The DMUs, which is the firms or the unit, are represented by N. And these N, they also are many because there are many of the DMUs. So they start from DMU1, DMU2, all the way. Okay, so it's J. Let me just tell you the exact name. I just want to use the right one. So if DMU is a J, and the J starts from 1 all the way to N. So N here is the total number of firms or DMUs, and each one is a J. But at each point, when you're talking about one particular one, you can use the number naught, 0, okay, or 0 naught to represent the target DM. To represent the target DM. Your appreciation of this is important. Okay. So watch the keywords I'm using here. So the N, the DMUs, they produce S non-negative output. Non-negative means that you don't want any negativity. So you can have 0 output. And what is the output? The output is Y. And the Y is a member of a real positive alternate. And they are consuming the M. The M, I told you that the M is the total number of the inputs, okay, input I, which start from 1 all the way to M. And these M2 are non-negative, okay, and they are for the input, and each input is a member of the real positive alternate. So that is a real number here that we are talking about. So given all of this, and when you are writing your thesis, this is a standard beginning. Given all of this, then we can say that the production technology set, which is made up of the input-output combinations, these different input-output combinations can now be summarized as phi, which is made up of the input-output combination, which is a member of the real positive and negative input and output alternates, whereby X can produce the Y. Okay. So this whole Hebrew, you might call it, is representing the technology set. When people are developing models, this is where they start from. When you are not developing models, this is where you also start. Okay. So now, inside the technology, certain things are happening. X is producing the Y. Y is consuming the X, and so many things are happening. That is why you see it in the set, you know, in that curly bracket set. You know, it's a set of information that is going on there. Now, how do you now define efficiency? Efficiency generally, and this is coming from last time, efficiency generally is made up of output over input. Okay, output over, you guys remember that the last time we met, we actually defined efficiency as output over input. Okay. Please, for those of you, somebody should put it on the page that we've started so that the rest will know. So it's output over input. So if your output is 10 and your input is 5, then your efficiency is equal to what? You can tell me. You can tell me. If your output is 5, output is 10, and your input is 5, Salina, what is your efficiency? Which one? 2. It's 2. Okay. Now, what it means is that That 2 is your y divided by x. But note that the definition of y divided by s, that definition is a single kind of definition, y over x. It's not multiple, but I've already indicated that in real life systems, things are not single. But we know that the only way you can increase that output, that efficiency, is by increasing the y or reducing the x. That's how we know it. Then the ratio will go up. And that is a single input, a single output efficiency definition, which means that we are assuming that there is constant returns to scale. But in real market systems, firms use multiple inputs and multiple outputs. And so how do you now measure efficiency? Instead of y over x. This is the interesting part. What this now means is that you need to now weight the input. Look at the word I use, weight. Attach importance. Give me a weight. For example, if you are in a company, and in that company, you have laborers, you have cleaners, you have clerks, you have supervisors, you have managers. And the total number of workers are, say, 10. You will not use that 10 to indicate that because the total number of workers are 10, everybody is equal in terms of his effort he brings into the company. Obviously, the CEO brings more to the company than the rest. So when you add attaching importance to people, of course, the money that each person gets reflects that person's importance. So you attach enough importance to those that you find to be valuable, much more valuable. So that is what I mean by the weight. So in order to be able to estimate efficiency under complex situations, the y over x will have to be the weighted sum of the output over the weighted sum of the input. Now, ideally, watch it. Ideally, somebody should say that, somebody might have said that, really, it should simply be output. This is the singular definition. Efficiency is output over input. But in a multiple situation, the person would say the efficiency is y1 plus y2 plus y3, okay, all the way up to, let's say, yk, divided by the input, which is x1 plus x2 plus x3, all the way up to what? Xk. Now, there's a problem with this if you define efficiency like this. Because what you've done is that you've just combined, by using the principle of additivity, you've just combined the inputs and the outputs together. Because you say there are multiple inputs and multiple outputs. So because of that, you just combine them together and that's it. No, no. The y1 might be more important than the y2. And the y2 might be more important than the y3. And the x1 might be more important. So each of the inputs and each of the output has to be weighted. So what you are having here right now is not correct. If I want to add the inputs and the outputs together, I need to weight them. So what is the weight? The weight is the importance. So I need to attach some importance. And this importance, they have names that we give to them. They have names, okay, that we give to them. And as you attach the importance to them, okay, they are gradually moving towards a proper definition of efficiency. If you don't understand clearly, let me know. So if you watch the definition, efficiency is not just the sum of outputs over the sum of inputs. No, 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 no. It is a weighted sum of outputs over the weighted sum of inputs. Weighted importance. Okay, so now let's attach that. So you can see that now with the output y1, I am attaching a weight y1 u1 with output y2, I'm attaching the weight input u2 up to output ys. I will attach the weight called us. So there's a weighted output over the weighted input, and each of the input is also weighted with v1, v2, v all the way. Now, what are these weights? The weights, we call them the multipliers. You come to understand them later on. The multipliers. Now, please note something. Whenever you multiply the weight by the variable, whether it's an output or it's an input, whenever you multiply the weight by the variable, that is called virtual output or virtual input. Virtual output or virtual input. When you multiply the u by the y, what you have is called a virtual output. The weight, the importance. Now, if you have done DEA, and Professor Podinowski makes this clear, well, that every DEA model, there's a primal version and there's a dual version. The primal version, and you later learn this, the primal version is said to be the envelopment model. And the dual is known as a multiplier model. The dual, okay, that's the one that will attach the weight here. So what you see up there is a dual. The dual will assess efficiency of the unit in terms of the ratio. And as you can see up here, you have ratio. Ratio of the aggregated, that word aggregated is the same as the sum. So instead of using the sum, we now use aggregated weighted output to the aggregated weighted input. Okay, in relation to, and this is important because we are going to do something, relative to similar ratios calculated for all observed frames. Now, if you look at this definition I've given a general definition of efficiency. I was not really saying the efficiency of a particular DMU. I just gave a general definition, as you can see up here. Now let's be specific. Let's assume that we want to talk about a particular DMU whose efficiency you want to assess. So what we do is this, before we come to that mathematical formula. In order for the DMU's efficiency to be estimated, and let me go back up here, you need to allow that DMU to choose the weight, the importance of that particular variable. So let's say that the variable is y1, y2, y3. That DMU A will have to select how much importance that it wants to give to that particular output. So if you take a particular bank, the bank will, in the DEA framework, in the model, it's been designed in such a way that the bank, EcoBank, will select labor, deposit, capital, equity, investment, CSR. It will select each one of these as it sees it important. In other words, Ghana Commercial Bank may want to attach a lot of importance to loans and advances. I didn't say it want to attach all the importance. So I said a lot of importance. Remember, the word importance here is always between 0 and 1. It is a percentage value. The weight is between 0 and 1. It's a percentage. So you have 100%. Now, you got to distribute 100% in such a way that you assign some importance, some percentage to some of the input. But a particular bank can say that as for it, it sees only the investment as important and all the rest are not important. All right, fine, fair enough. If that is going to make you efficient, if that is going to make your ratio higher, that's okay. So the situation where you allow the firms to choose their own importance weight, that is good. Why is that good? That is good because it allows every firm to have the freedom of choice to decide on whatever input it wants to use, so that no particular firm comes to complain later. Oh no, I am not efficient because you impose that importance to my deposit when I didn't want to put a lot of importance to my deposit. You guys understand? And so you give each firm the freedom of choice to select any important. So there is that flexibility for each firm. But when you sometimes, in different models, when you restrict the firms from assigning some weight to some particular variables, when you restrict, this is known as weight restrictions. This is called weight restrictions or trade-offs. And when that happens, okay, you have not allowed the firm to look as good as possible as he wants to do. But when we take away the weight restrictions, managers of those firms cannot easily reject the results as being unfair because they have been allowed to select the weight that will put them in the best possible light as possible. So weight is important, and the DEA model is designed to allow the firms to select those weights. Now, the input and output weight in the equation that you saw, those input and output weight, the U1, the U2, the V1, the V2, they are found, they are obtained. They are the solution to the linear programming or the mathematical programming that you would have solved. So now, let me show you the mathematical program. Okay, remember, we are going to do it for each firm. Ideally, what you do is that you formulate this model for each firm. So if the firms are 5, you're going to formulate the model for each one of the firms. And I'm going to show you in this course how to formulate the model using our hypothetical firms. Are you okay? Okay. So I'm going to be showing you that. I'm going to be showing you. So get ready for learning about. But first, let me give you the general one. General formulation. Now, this general formulation, when you show it like this, sometimes a person might think it's Hebrew, and the person might want to collapse. But don't collapse at all. It's a beautiful thing. First of all, this is not linear because it is a ratio. That's all I want to say first. So it's a non-linear fractional programming problem. But sometimes later on we'll move to the linear programming problem. But this is a non-linear programming problem. What is this? What is this saying? What it is saying is this, that the efficiency of a particular firm, I'm using that number there for you to see. The efficiency of any firm, and what is that firm? The firm here is not, is a targeted firm. So we are representing it with not, 0. The efficiency of that targeted firm can be obtained after you have maximized this number, which happens to be equal to the weighted sum of the output. So you see, what I did is that if you look at the output, this formulation was done by Charnes-Cooper and Rhodes. And what they did is that the U1 multiplying the Y1, the U2 multiplying the Y2. But now what we're doing is that we are summing all of them together. So we know that the U's, they are from, each one of them is an output, and they start from 1 to S. Okay, they are R. Look at the bottom here, you see some. They are R starting from 1 to S. So now we are putting all of them together. So that's why we are bringing the summation sign. So you can see that the summation sign shows that it's from 1 to S. So we are summing all of the outputs together. divided by the sum of all, the weighted sum of all the inputs. Now, that is for a particular firm, that targeted firm. How do I know it's for a particular firm? It's because of the knot. So check and note that the knot indicates that it is a targeted firm. Now, so we are maximizing this ratio. But don't forget it, there are certain conditions you got to fulfill. And what is the condition? The condition says that if that same ratio for all the firms, remember, I am trying to maximize the efficiency of this particular targeted firm by assigning some weights. If the same weights are applied to all the firms, including even that firm that was part of it, including even the targeted firm. This time, you see, there was no knot here in the second one under the subject to. There was a J, and we know that J represents all the firms from 1 to N. So I am maximizing this ratio under the condition that if the same weights are applied to all the firms, they must not be greater than the user-specific value of 1. It mustn't be 1. In other words, the weight must be 100%. That's what you're trying to say. The maximum number of the weight must be 100%, which means it can be less than 100%, but the maximum must be 100%. And you can see that there is a second condition, which is a non-negativity constraint in normal programming. And that second condition says that the weight for the output and the weight for the input must be 0 or more. The weight, in other words, there must be non-negative weight. So this is it. Now, I want you to check something very carefully here. Whether you are doing input orientation or output orientation can change the way you formulate the model. So I want you to pay attention here. Okay. Now, in this model that you are seeing here, let me share something. In this model that you are seeing here, watch carefully, and you will notice that we are the output is at the top. We are maximizing the weighted output, the sum of the weighted output over the sum of the weighted input. That is an output orientation. Anytime you have that ratio starting with the output at the top, that is an output orientation. Even when you come to the constraint with the output at the top, that is an output orientation. But how would you know that is an input orientation you're dealing with? Well, that one, look at the second one here. The input weight is at the top. The weighted input, the sum of the weighted input is at the top. So that is when you know that you are dealing with what? An input orientation. So in an input orientation, you don't maximize, you minimize the ratio. Subject to the same thing, but this time, because it's an input orientation, the ratio condition for all the other firms must be greater or equal to 1, unlike the previous one for input-output orientation when it was less than or equal to 1. For input orientation, it will be greater than or equal to 1. I hope you understand. This is important. Okay, so output orientation, the way you formulate it is slightly different from the input, and it's more a matter of taking reciprocals of things. If you check carefully, if you check the ratio, it's just the numerator coming down to the denominator coming, numerator going up, denominator coming down. Okay. It's just swapping them for input and output orientation. So get the understanding clear and know which model you are dealing with. Okay. Now, everything I've said is in the notes here. Okay, what the whole thing, it says that efficiency equals the maximum of the ratio of output over input, subject to the condition that if the same ratios, okay, similar ratios for every firm must be less than or equal to the 100% when the same values are applied to each unit, just as I indicated. In other words, somebody might say that why are you making it less than or equal to 1 or greater than or equal to 1 for the input orientation? Why are you doing that That inequality symbol. Well, if that was not there, if that subject to that constraint was not there, then what it means is that nothing is going to prevent that particular DMU from selecting so big a weight. Like picking a weight, you're going to pick a particular weight to be 80%, then you pick another one to be 80%, then you pick another one to be, no, there must be a limit. But if you don't bring that limitation, you're not preventing them from choosing weights. No. Such that the ratio becomes infinitely large. Because if this is not limited, the ratio is going to be very, very large. It is a weight that constrains the ratio to be within the 100%. So DMUs can only choose weights such that no DMUs have an efficiency score greater than 1 for the output orientation formulation. That is why we bring the inequality symbol. But life is not always fractional. Life is not fractional. And so these guys, these great authors, what they decided to do was to linearize this fractional programming problem by normalizing them. They use something that is known as a Charnes-Cooper transformation, okay, which is a linear programming algorithm, formulation from the days of Danzig. So they take that linear Charnes-Cooper transformation, which is again in the book by Charnes and Cooper, and then use that to convert a fractional program to a linear program. Guys, this is not difficult. You remember the good old days when you used to convert improper fraction to mixed fraction, or mixed fraction to improper fraction, and then you can now have certain things like that. That's the similar thing here. But here, you are converting the whole thing from fraction to linear. And how do you do that? Well, if you are dealing with the input-oriented, okay, and when I say input-oriented, I'm talking about this one, the one on the far right here. If you are dealing with the input-oriented, remember in the input-oriented, you are minimizing the input over the output. If you are dealing with that input-oriented, okay, then it means that you can linearize that fractional program by normalizing the weighted input. So what you do is that in the input-oriented, you normalize the input by setting it equal to 1. That's what we mean by normalizing, or any constant. And then you minimize the numerator. Okay. You minimize the numerator there. So if it is an output orientation, you have to normalize the output, which happens to be the numerator, by setting the output to 1, and then you minimize the denominator. Don't get confused. So I'm going to do the output oriented one. Okay, so let's go to the output oriented. This is the output oriented one. The output oriented one says weighted output divided by weighted input. And then of course the same thing, but this time for all other DMUs, subject to that constraint, which is less than a 1 user specific bound. So what it means is that because we are dealing with output oriented here, we are going to set the output to 1. So summation R all the way from 1 to S, UR, YR naught, okay, we're going to set that to what? 1. Oh, sorry, when you are doing the output oriented, okay, you're going to set that one, yeah, you're going to set that one to 1 here. And then this very 1, which is the denominator here, you're going to minimize it. You will set the numerator to 1 and take it to the constraint. You bring it to the constraint down here. And if the constraint 2 will have to be linearized. How do you linearize something like this? I'll show you. Okay, let me just show you. Okay. This is normally something that I don't do, but I want to just make it as simple as possible so that those of you who are slightly thinking that we are speaking Hebrew will not be worried. Suppose you have A over B equals to maybe 1. That is how it is there. Okay. Now, the only way you can linearize this thing is do cross multiply, first of all. Okay. So cross multiply, you get A equals to B. And then bring the B to the left side. So you get A minus B, and then you are left with 0. Okay. So basically, that's what you're going to do for this. And this one is now in a linear form. So that is now in a linear form. Let's do that in there. So we are going to take this value, the numerator, okay, and then we're going to set the numerator to 1, and then we maximize the denominator. This is how it becomes. So you minimize the denominator. You minimize this denominator. Remember, when you go and check, you notice that the denominator was the Vx, the Vx. So that's the one we are going to minimize. Okay, and then we'll add plus omega, W to it. I'll come and talk about this omega soon, but for now you can assume in your head that it's not there. Okay, so we are minimizing this denominator, which was up there, by setting the numerator to 1. You see down, look into the constraint. In the constraint, we set the numerator to 1. Okay, we set that numerator to a value of what? A value of 1. So this numerator is set to 1. That was in the numerator of the fraction. Okay, and then we indicated also that the ratio, all right, the ratio which was in the constraint, and then again, when you go to the constraint, you see that the constraint was something like A over B that I showed. So that A over B, the 1, when you do the cross multiply, the B will multiply the 1, and then you bring that 1 to the left hand side. That is how come it is now a minus. So it is like multiplying both sides by minus that summation in the circle here. Multiplying both sides. And when you do that, that will switch the inequality sign. Okay. The sign was less than or equal to, but I will take it to greater than or equal to. And that is how come you now see the sign as greater than or equal to. So you can see that this whole fraction is now linearized. And then the fraction at the top has been made linear, and the other part has entered the constraint in there. You set the constraint to 1 because that's a 1, you are normalized. Anytime in a multiplier model like this, the one that is set to 1 will tell you the orientation. And when you look at the content, since it is output, it means that this is an output orientation. Anytime the one set to 1. If it happens to be an input, then it means that you are dealing with an input orientation. Okay, now what is the W? Well, the W will tell you the type of returns to scale we are dealing with. Remember the last time we looked at the different kinds of returns to scale. We'll come into the full details of returns to scale. But when the returns to scale is constant returns or variable returns, if it is constant returns, then this omega will be 0. So everything falls away. But if it is variable returns, and one of the things you understood about variable returns is that variable returns means that you can be having what? You can be having constant returns, decreasing returns to scale, or increasing returns to scale. All of them are part of the variable returns to scale. Now, if the W, because the W is indicating that particular firm, its location in the production possibility set, the returns to scale that it is exhibiting within. So it's more or less telling you the local returns to scale. Where is it located in the set? Now, if this value is less than 0, that is, if it's negative, then that firm is located in an area known as the decreasing returns to scale, if this value is less than 0. But if this value is more than 0, it's positive, then it is exhibiting, that firm is exhibiting increasing returns to scale. Okay, then that firm is exhibiting increasing. And if it is equal to 0, I've already said it, it means that the firm is exhibiting constant returns to scale. And most softwares will do this for you. All right. So that is how you linearize. So my advice, I want you to do this and give it to me next time. Go and take the input orientation fractional programming and rewrite it as a linearized form like this, a multiplier linearized form like this. And then come and show me, for that input oriented. What I've done here is for the output oriented. But please know that in an output oriented, when you have linearized it, you use the word min. Okay, you don't use output, you use the word minimize. So that is how you do the formulation. The most important thing is note that this is a linear form than a fractional form. Okay. Now, the interpretation is this. Of course, we'll come to the interpretation, but I want you to know something very important about the duality. Now, remember I told you that in a normal linear programming model, again, you can actually unmute yourself and ask a question. What was the question you said I should repeat? In a normal linear...
No, I think it's okay. You were talking about the normalizations with respect to the input orientation, and
it's clear now.
Yeah, it's clear.
All right. Every linear program model, and guys, I'm going to end here, so I want you to pay attention here. Every linear program model has a primal model and a dual. The best way, like I said, you can look at it is, if you look at the way most of you have done microeconomic theory, where we now can use the principle of Euler's identity, Roy's identity, and we can connect the Slasky equation between minimization and maximization. In fact, you can use the principle of duality to convert a profit maximizing model, a revenue maximizing model, to a cost minimizing model. It's the same principle that we use to connect production theory to cost theory. Whereas one is looking like that for the production, one is looking like that for the cost, the U-shaped nature of the cost curves. So every linear program model can be converted into a primal, and a primal can be converted into a dual, and a dual can be converted into a primal. Okay? You just have to decide which one is your primal, and by the complementary slackness approach, you can now come out with the rest. So the same thing in DEA, because in DEA, one of the model is known as, the primal model is known as the envelopment model. Envelopment. Okay, that's the name for the envelopment DEA. And then the dual is known as a multiplier. That's the one we are dealing with some few minutes ago, the multiplier model. Okay, so I just want you to know the difference between the dual for the DEA and the primal, or the envelopment and then the multiplier. That way, when you see it, you will notice it. But please know that most of the papers will not be talking about the multiplier. No, most papers don't use the multiplier model, except those that are dealing a lot with the weight restrictions and the trade-offs and several other things. But other than that, majority of the papers will be dealing with what? They will be using the envelopment model, the envelopment. But the one we just finished with is a multiplier model. So how do we turn it into the envelopment model? I'm not going to go into the nitty-gritties of all of these things. It's not really the ultimate. Yes, Salina, ask a question.
All right, then. So thank you. Please, I want to ask that when we are totality, how do you reverse the formula or you reverse the input? I don't know how it to play in the formula.
When you are doing what?
Reverse causality.
Oh, no, you don't need that here. That word reverse causality has to do only with regression. Don't connect anything to your thesis yet. Okay, just enjoy the learning. Yeah, enjoy the learning. There are several things you are learning. Okay, so just enjoy the learning, detach yourself and connecting it with your thesis. There is nothing, the word reverse causality here has to do with regression. That's what we are doing. We are doing DEA here. Okay.
Okay, thank you.
So primal model is an envelopment model. Dual is a multiplier model. The dual will convert the minimization into a maximization. That's what you want to know. The dual will convert it. So if it is a maximization, the dual would simply make it minimization. And for those of you who have done linear programming, you know what. So let me give you the Farrell general model, envelopment model, which is just like the one you saw before. So it's just like this one. So I'm now giving you, this is a multiplier model. I'm now giving you the dual version of this, which is the envelopment. Okay, envelopment linear programming model. When I actually show you a certain table, you will see how what each one means in the envelopment, what each one here in the multiplier means in the envelope. So this is how it becomes. This is the output-oriented envelopment model. I've just called it a VRS. And I'll show you why I called it a VRS. If it wasn't the VRS, it would have been what? If it wasn't the VRS. If it wasn't the variable returns to scale, then it is what?
The constant return to scale.
Constant return to scale. So now, what makes it variable returns to scale? It is the last constraint. Well, the last but one constraint, the one at the bottom here. That's what makes it variable return, this one. So once you remove that, once that summation lambda j equal to 1 doesn't come in, then we have constant return to scale. So once that one is deleted, once this one is deleted, then we have a constant return to scale. Okay. Now, what does it say? Because it's an output orientation, we'll use the word this phi for it. We use this phi for it. Well, which means that the other one I spoke about wasn't the phi. Yeah, I want to clarify this one because the name I use, if you don't take it, you will miss it. This symbol is PSI, psi. Okay. Normally we don't even mention the P, so it's psi. It's that is for the technology set. Okay. That is for this symbol for the technology, PSI, psi. But the one that I'm showing you in the formulation here is phi, 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 PHI. Okay. So take note that this one is phi, and it is an output-oriented efficiency score. Why is it star? The star here means the value has been obtained. I'm explaining this model very carefully to you so that you always never miss it. So what it means is that the value of the output-oriented efficiency score, let's call that value, say, 1.2. And please remember, we said that the output-oriented efficiency score is between 1 and above. Okay, we said it's 1 and above. Okay, and when it is above, it's inefficient. So let's say that a particular value is 1.2. That is a 5-star. But before you can get this 5-star, you need to maximize a 5. Okay, you need to maximize a 5 subject to the condition that the lambda condition, which we are going to talk about very soon, for each DMU, under the condition that the weighted sum of the input of all firms, and I mean all firms, the weighted sum of the input of all firms is less than the input of the DMU under evaluation. Now, why do I use the word under evaluation? The DMU under evaluation. Well, the DMU under evaluation because we are talking about a not, a targeted DMU. So anytime you see that we have XI naught, that is different from XIJ. The I naught means the particular DMU, the target DMU. Okay. So what you are saying is that the weighted sum of the inputs, these are the input of all the firms, not only the target you are dealing with, but all the firms. So this whole thing on the left-hand side here is the technology. So that's why you see it is a sum, and it is from 1 to n for all the firms. So the weighted sum, now what is the weight? The weight is that lambda symbol. That symbol here is a lambda. So what is that thing saying? It's saying that if we are to weight all the input, and we'll mathematically write this as we go further. If we are to weight all the input, if we are to attach importance to all the input, that's the convexity assumption. That's a linear combination, okay? That's a linear combination. So the X1, all the inputs, if you have to weight all the input and we sum them, after weighting, we sum them, okay? They should be less than the input of the DMU whose efficiency you are currently trying to maximize. Remember, you do for each DMU one at a time. You do for each DMU one at a time. Of course, the software does it immediately for you. So what this one is saying is that maximize this phi, the phi is efficiency score, and get the actual number, which is a 5-star, but subject to the condition that the weighted sum of the inputs of all the other DMUs is less than the input of the DMU under consideration. Okay. And also the weighted sum of the output, not just the input, but the output of all the DMUs is greater, not less than, is greater than or equal to the output of the DMU under evaluation. Okay. So for you to know that the DMU under evaluation, you bring the 0, the not attached. Now, you can see that the phi has been attached to the output. The phi, which is now in blue color here, has been attached to the output. It was not attached to the input up there. That will tell you that we are dealing with the output orientation and not the input orientation. Okay, that means that you are dealing with the output orientation. You are not dealing with the input orientation. So what this formulation, this envelopment model is trying to say, forget about the last one. The last one is just the returns to scale assumption, which I told you that it can be constant returns when the whole thing is not there. So what this one is saying is that in order to get, in short, in order to get the output-oriented efficiency score for a particular DMU, you need to take into consideration this, the same thing, the same weight if they were attached for all the other firms. Now, I will come back and I come and explain this lambda very well later on. But I want you to know that the lambda is an intensity weight. The intensity, the weight. So in other words, this is a benchmarking exercise. This is a benchmarking exercise. In other words, the efficiency score of any particular firm is a relative score. It's a relative score because your efficiency is being measured relative to the boundary of the production possibility set. So your score is dependent on the entire set is boundary. That is why it's a relative measure. And so the fact that you have these one, I told you earlier that the things on the left-hand side represent the entire technology set. So the entire technology set is on the left-hand side here. So everybody's efficiency will be measured relative to that set. And the lambdas help you to combine the set together. The lambdas are helping you because they are adopting the principle of the convexity assumption. Remember, the convexity assumption says that if a particular point is feasible and another particular point is also feasible, then a linear combination of them is feasible. That word linear, combination, linear, that is what, that thing which is linearly helping you to combine them is the lambda. And so, but why are you using the lambda? The lambda is telling you the amount of importance that you are attaching to a particular DMU in helping you to become efficient. So EcoBank can say that I'm a very efficient bank. But EcoBank will attach importance to all the firms in the industry. Those that it sees as very important, it will attach more lambda weight, more importance to them. And so EcoBank's efficiency score eventually will be a reflection of the entire situation that is in the industry. And so the efficiency is a benchmarking exercise. It's a relative measure. Your performance depends on the industry's, the entire possibility, the entire technology set. Because your performance was measured relative to an unobserved frontier. And because it was unobserved, you have used the data which you observe to create a frontier. And then you are measuring your performance in relation to that frontier. Because you are measuring it relative, it's a relative efficiency measure. And those mumbo jumbos on the left are the things that help you. Regarding the structure of the frontier, will be dependent on that last constraint. So if the frontier is going to be a straight line, then that is constant retention scale. In that case, this one is not there. The VRS constraint is not there. But if it is going to be like piecewise, then that is a VRS. That is when we have this constraint there. Now, the last constraint you see here is again the intensity, the weight. That is the non-negativity constraint. So what it's saying is that the importance that you are attaching to each DMU's effort, the weight is 0 or more. Okay, is 0 or more. All other things have been defined as it is. Now, you will later learn that this lambda, this intensity constraint, has some connection to do with the U and the V that are in the multiplier models. Okay, we have some connections with that. But I don't want to bore you so much with those areas because, like I said, majority of studies, we don't look at the multiplier model. Okay. In the deep learning, I can show you how the multiplier model actually works with that because there's a whole note I have on the multiplier model. But I want you to understand the key elements, the targeted DMU, the phi, the lambda, the summation. Now, the only way for you to understand this general, when I say general, we are using Greek names and English names. But when we now start putting numbers into them, oh, believe you me, you are going to have a beautiful understanding of everything in there. So, some few things about what you've done. Okay? That the XI nodes are the I've and the R's output of that particular DMU. Okay. Secondly, the 5 star is the output-oriented score, is a number. When it is 1, it means that the DMU is efficient. Okay, it means that the current output cannot be increased further, radially speaking, which means that the DMU is on the frontier. But when it is bigger than 1 in an output orientation, it means that that firm is dominated or is inefficient. And the details of the model, I've explained it all, how it all works as this. I've explained that. All right. Any question before we go to scale efficiency? Any question on this? It is under weight restrictions that a multiplier models become much more interesting and apparent. Okay. When you want to do target setting, the envelopment model is good. The envelopment model helps you to interpret efficiency scores easily. And it also helps you in target setting. The multiplier model is very good for trade-offs and weight restrictions. Other than that, you will not want to specialize for now. You wouldn't want to be specializing a lot in the multiplier model. But unless you go further, you begin to have further knowledge, then you can now enhance your mind on that. So that is the main difference between the multiplier and model. The key point is that I'm going to dig deeper into the envelopment model. The multiplier model, I'm done with it now with you guys. Okay, I'm going to take a data set and I'm going to show you how you will formulate that data set in an envelopment model. We'll do for both input orientation and output orientation and non-orientation, we do for that. So that when you also create your own hypothetical data set, you'll be able to do the same.